Before we understand the central limit theorem, we need to grasp one fundamental concept: the difference between a population and a sample. The population represents all possible data points in the universe we're studying. But here's the catch: we almost never have access to the entire population. Instead, we collect a sample, a smaller subset that we actually observe and measure. From this limited sample, we try to estimate the true population parameters. This is the foundation of statistical inference and machine learning.
Now, here's where it gets interesting. What happens if we don't just take one sample, but many samples? Each time we collect a new sample, we calculate its mean. Do this 50 times, 100 times, and something remarkable emerges. Those sample means start forming their own distribution. Watch as we repeatedly sample from our population and plot each mean. Notice how they begin clustering around a central value. This distribution of sample means is the key to understanding the central limit theorem.
Here's the magic of the central limit theorem. It doesn't matter what shape your original population has: uniform, exponential, bimodal, literally any distribution. When you take the means of repeated samples, those means will always form a normal distribution. Look at these three completely different population shapes. As we sample from each and collect the means, they all converge to that beautiful bell curve. This universality is what makes CLT so powerful. The formula, sigma over square root n, tells us exactly how spread out those sample means will be. Let's talk about sample size, because this is where CLT becomes practical. Look at what happens when we vary n, the number of observations in each sample. With just 5 data points, our sample means are all over the place, a wide, uncertain distribution. Increase to 30 and the distribution tightens significantly. At 100 samples, it becomes remarkably narrow. This is the standard error formula in action: sigma divided by square root of n. The key insight? More data means less uncertainty about your estimates. But notice the square root. You get diminishing returns. Going from 5 to 30 helps a lot, from 30 to 100 less so. Let's see CLT working with real-world data. Consider server response times, something every ML engineer deals with. The raw data is heavily right-skewed. Most requests are fast, but some outliers take forever. This is clearly not a normal distribution. Now watch what happens when we repeatedly sample 30 response times and compute their means. Despite starting with this ugly, skewed mess, the sample means form a beautiful bell curve. This is the power of CLT in practice. It transforms chaotic, non-normal real-world data into something we can work with mathematically. This is why so many statistical methods just work, even when data looks messy. So why should you, as an ML engineer, care about the central limit theorem? Because it's everywhere in your daily work. When you calculate confidence intervals for your model's accuracy, CLT is behind the math. Running A/B tests to compare two models, CLT lets you determine statistical significance. Cross-validation scores across folds, they follow a normal distribution because of CLT. Even ensemble methods and distributed training leverage this principle. When you average predictions from multiple models or gradients across GPU workers, CLT explains why this reduces variance. Understanding CLT isn't just theory, it's a practical superpower for building reliable machine learning systems.